Good afternoon, ladies and gentlemen. On behalf of ISHRAE, India Cooling Coalition, Solar Decathlon India, and Alliance for an Energy Efficient Economy, I, Rashi Sharma, welcome all of you to the webinar on Integrative Design and Advanced Energy Efficiency, Unlocking Affordable Cost Savings and Decarbonization. Thank you for joining us today. In today's insightful discussion, we will delve deeper into the electrification drive in the United States with our esteemed guest speaker, Mr. Peter Rumsey, fellow AEEE, founder and CEO of Point Energy Innovations, who will share his invaluable insights and experience gained from his direct involvement with Infosys India on their journey to reduce their energy use by 50% and decarbonization. It is with great honor that I introduce our distinguished guest speaker, Mr. Peter Rumsey. With a career spanning several decades, Mr. Rumsey is a globally renowned expert in energy efficiency and sustainable building system design. He has been at the forefront of innovation in energy efficient design and analysis. His groundbreaking work includes pioneering technologies such as chilled heat, radiant cooling systems, low pressure drop systems in US laboratories, and the introduction of guaranteed performance contracts for HVAC systems. Notably, Mr. Rumsey's portfolio boasts a remarkable track record, having successfully directed the design of 17 LEED Platinum certified projects, 3 Living Building Challenge, and 15 Net Zero projects. His unwavering commitment to making environmentally sustainable solutions economically feasible and practical has led to the establishment of Point Energy Innovation. His visionary firm seeks to redefine the landscape of delivering net zero and high-performance buildings, testament to his resolute commitment to a greener and more sustainable future. We are privileged to have him with us today, and we look forward to the profound insights he will share. We welcome you, sir. I will now pass the floor to Mr. Rumsey, but before I do, I'd like to inform our participants that a dedicated Q&A session will be held post Mr. Rumsey's presentation, during which the participants are encouraged to raise their hands virtually or drop their questions in the chat box and unmute themselves once called upon to ask their questions to Mr. Rumsey. Over to you, Mr. Rumsey.
Great. Thank you very much. And I would like to start by apologizing for the delay in getting started. We had a software glitch on our Microsoft Teams, unfortunately, but now we're back online, ready to go. So I want to thank everybody for being here today, and I wanted to share with you some of my experience in designing advanced energy efficient buildings, and also the idea of unlocking affordable, cost efficient and decarbonized buildings. So if we could go to the next slide. I do want to let you know that in addition to being a consultant, I also am a lecturer at Stanford University and the founder of the Stanford Building Decarbonization Learning Accelerator, which creates free teaching resources for university professors to be able to teach building decarbonization. And I would recommend or welcome you to visit our website and look at the material that we have there. And for those of you who are teaching at the university level, you might find some useful information. I first started working in India 15 years ago with Infosys on the SDB1 project, which was there in Hyderabad, which was their first building of trying to go far beyond and figure out how to make a building very energy efficient and at the same time affordable, and creating very high performance workplace for their employees. And we wrote several articles about that after it was done, and learned a lot from that. Now that building was the beginning of Infosys's journey in developing a whole generation of very high performing and low energy buildings. Infosys, as you might or might not know, now has cut their energy consumption per employee in half over the last 15 years. So it's, as far as I know, the largest and most successful corporate energy efficiency program in history. I want to jump in and talk about building decarbonization, because for the longest time we've been very focused on how do we make buildings more efficient, but I think we're now expanding the discussion and getting more focused at the same time on what do we need to achieve here. Yes, lower energy efficiency, but really the prize is being able to decarbonize buildings. The carbon impact of buildings is made up of two different things. One is the embodied carbon, and the other is the operational carbon. Embodied carbon is the carbon that's emitted when we manufacture, transport, and install building materials in buildings. Operational carbon comes from the emissions of building energy use. Generally speaking, when we look at it at a societal level, operational carbon dominates the carbon impact of buildings, usually by a 3-to-1 ratio. Globally, buildings account for approximately 40% of overall greenhouse gas emissions. Very significant. And as people involved in the building industry, we have the opportunity to impact a large part of the global emissions on carbon. So we start thinking about the operational carbon, and that's the carbon emissions related to building energy consumption. The steps for decarbonization are fairly straightforward and simple. The first thing that we need to do is we need to design buildings that are energy efficient. I'm going to spend a lot of time talking about that today. Energy efficiency is the unsung hero of building decarbonization, and it's been so for many years. Once we make buildings energy efficient, and there's a lot of opportunity there, we need to electrify our buildings. That is, we need to have all of the energy consumption in the building to be electric. And then finally, we want to connect the all-electric efficient building to renewable energy that's generated either at the building or on the grid. And by renewable energy, I mean primarily wind and solar. So let's get in a little bit to this idea of advanced energy efficiency. The headlines, generally speaking, when we look at newspapers about energy issues and sustainably, it's dominated by solar energy and renewable energy. And I once had a regulator who spent her whole life working on energy issues say, Peter, you have to understand that solar energy is sexy, but energy efficiency will never get the headline. And she told me that quite some time ago, and I sense that is rung to be very true. So we will talk a little bit about solar and batteries, but I want to spend time talking about the unsung hero. A colleague of mine at Stanford University named Jim Sweeney conducted a 5-year study with his graduate students. It's super extensive look at energy consumption in the US over a 60-year period, that is 1950 through 2015. And what they did is they looked at each sector of the economy and looked at the energy efficiency of that sector. So they looked at buildings, they looked at transportation, aviation, industrial uses, and they compared the energy performance per unit of productivity. And for aviation, for example, is how much aviation fuel we're using to transport a person 1,000 miles. And what they found is they looked at every sector of the economy and put it together, that from 1975 to 2015, that energy efficiency was responsible for meeting a third of the US's required energy demand. And what that means is if energy efficiency had not been there, we would have needed 30% more energy. That energy efficiency meeting 30% of our demand was more significant than all of the solar, wind, and nuclear power put together that was built during that same period. Okay, so that was a 40-year period. So energy efficiency, in fact, not only has it been the biggest source of meeting our growing demand, but it's also one that is the cheapest way of meeting demand and creates the most jobs. During this period, there's a wide range of energy efficiency blockbusters, things that have been very significant, but I did want to share a few of those that are particularly important in the building sector. LED lighting is something that we all now know and hopefully love. We were talking about that this morning, that that buying a non-LED bulb it's now hard to do. And the non-LED bulbs, like fluorescent bulbs or incandescent bulbs, when LEDs were first introduced, they were significantly more expensive, but now they've dropped 10 or 20-fold in price, and they provide better service, longer life, at very similar costs to what we were seeing before. Low emissivity glazing and windows, variable speed drives, VAV boxes, all of these things, if you put it together, the impact on building energy use is immeasurable. LED lights, there's been one estimate that LED lights so far have been responsible for reducing global energy demand by 200 power plants. Super, super significant. And again, it's the unsung hero. There is a whole next generation of energy efficiency blockbusters out there. I did want to share some of the more significant ones with you guys today, and we'll be talking about these and others. Integrative design is another one of these things that is a little bit of an unsung hero and oftentimes overlooked, but very impactful, and is being used in a wide variety of buildings. The idea of integrative design is that if we work together on designing buildings as a set of design professionals and talk to one another and try to find optimization in buildings, that the answers are oftentimes cross-disciplinary. For example, if we spend time talking about the building envelope and how to make that better, it might mean that we have to spend a little bit more in the architecture of a building, but we'll be spending less on the mechanical systems of a building, the heating and cooling systems. Here in India, mostly cooling. So one of the things I like to say is the best HVAC system is a better building envelope. So let me show you a couple examples of that. One of the projects that I have worked on is Rocky Mountain Institute's Innovation Center. And this is a building in the Rocky Mountains in a cold climate near Aspen, Colorado. And the building was designed in a way that the building envelope was highly optimized. There was optimal amount of insulation, optimized glazing. The glazing on the north side of the building on the left was smaller than on the south side. But you can see an image on the right. The south side had more glass because they want the sun in this climate. And they thought about thermal mass when the sun shines, have it hit thermal mass to be able to absorb the heat and hold it for the evenings. They even went as far as using heated and cooled chairs to provide better comfort to the employees in the building. So as a consequence of these optimizations on the building envelope, the heating and cooling system, when the engineers that were doing the design on this came to the table at the beginning, they had a very complex system. They had a ground source heat pump. There was a whole mechanical room in the building to house all that equipment. And then there was expensive distribution throughout the building. What we did through optimizing the building envelope, we eliminated the whole ground source heat pump system and the vast majority of the requirement for the mechanical room. So we like to call that the mega mechanical room. We were able to negate it, the need for it, by using the better building envelope, and then that opened up more space in the building for programmable areas. Same applies in hot climates. When we started working with emphasis on Hyderabad, we spent a lot of time thinking about the building envelope, and in Hyderabad the idea was not, we don't want the sun shining in the building, we want to shade the windows, but we still want daylight and view to come through those windows. So there was an effort to look at a wide variety of options, and there were many, and they decided on this one you see in the photograph. It's not the only one. There really are infinite solutions for this, but it allowed for the employees to have a view outside, but the direct sunlight was not coming in the window. And you can see this sunshade light shelf. The daylight window above the light shelf was able to bring the daylight into the space and bounce it deep into the space. So as a consequence, we were able to reduce the size of the HVAC system by 60%. So much smaller cooling system. The diesel generator system was for the whole building was reduced by 40%, and the transformers were also reduced by 40%. So significant savings on these costly systems that use energy throughout the life of the building and result in carbon emissions, and use that saved money to enhance and pay for the better building envelope. So shifting gears, let's just talk about heat pumps a little bit here. Heat pumps are revolutionizing the heating industry globally. Just as a little understanding on what heat pumps are, if we burn gas in a gas boiler or something similar, it will take 105 units of gas to produce 100 units of heat, generally speaking. But with a heat pump, it can take 1/3 of the number of units of electricity in. So 33 units of electricity goes in to create 100 units of heat energy coming out. And the reason why heat pumps can do that is they're able to pull heat from the surroundings, either water, air, primarily air, and transfer that into the refrigerant and ultimately into the air or water that's going into the building. As a consequence of the operating a heat pump, there is a waste product, cooling, that is sometimes useful depending on the situation. Heat pumps, the demand and the market for heat pumps has been exploding. This is the heat pump sales in Europe, and it's interesting to see that how heat pumps were already taking off before the war in Ukraine, and the reduction in natural gas availability in Europe. So these the heat pump sales have only accelerated in Europe. Heat pumps actually come in all shapes, sizes, and forms, from small residential sizes up to large industrial scale. This is a heat recovery chiller, and the beauty of this piece of equipment is it can make chilled water and hot water simultaneously. So again, shifting gears, I just want to quickly go through some of these blockbusters so you guys have a sense of it, and then we can have some discussion and you can ask a couple questions. But induction cooking is one of those things that's going to really revolutionize how we do cooking globally. We're familiar with gas stoves, and we're also familiar with electric resistance cooking. And electric resistance is the one that where we're heating the surface and the heat then goes into the pot. Electric induction is different. Electric induction uses a magnetic field to heat the pan directly, and it's not heating the surface of the stove, it's heating the pan directly. Gas stoves are generally in the neighborhood of 30, maybe 40% efficient. Electric resistance stoves are in the neighborhood of 70 efficient, so twice as good for electric resistance, but electric induction cooking is 80% efficient. So it's a significant improvement in efficiency. It also results in faster cooking times and more precise cooking. And here's just an image of that magnetic field where it's heating the pot directly. One of the things that we've found is that the cooking with gas in an enclosed kitchen does have a buildup of indoor air pollutants. One person was saying to me recently, if we measured the indoor air quality in a kitchen where they're using gas cooking, it'd be similar to a alert day outside. It's not the particulate, the PM stuff, but the nitrogen dioxide, NO2, and a recent study from Stanford also found that a high amount of benzene was being released. There's also formaldehyde and carbon monoxide that are released. So generally speaking, cooking with gas should not be done in an enclosed kitchen without having an exhaust fan on or a window open. Induction cooking is now available not only in residential scale, but all the way up to commercial scale, and even high-end restaurants are starting to use it. Not only is it better air quality, faster cooking, but it's also safer because you're not heating the surface around, and this results in less burns. And there's less waste heat, especially in commercial kitchens. So if you're a chef working at a stove all day long, you'll feel more comfortable. Another area that I think I see a huge growth for is using AI in building optimization. Buildings are generally, especially commercial buildings, are very dumb. And recently, 10 years ago, 15 years ago, Nest was born and started with a residential thermostat. It was, after a few years, bought by Google. And this is, in a sense, a shot across the bow of how we control buildings can be done so much more smartly, so much more intelligently. And we've only started to scratch the surface as far as what's possible in optimizing how we use energy in buildings. Commercial buildings are somewhat obvious that there's so many things that are not working properly in large buildings. The heating and cooling system is not, the cooling or the cooling only system is not set up in a way that delivers consistent comfort, or doesn't come on and off at the right time, or it's not optimized. But also, what we're going to need in the future as we have more and more solar energy on the grid is flexible demand. And we're going to be able to use artificial intelligence to manage how and when we're using energy in buildings, so that we're using energy in buildings when it's cheapest and when it's lowest carbon. For example, when we have a lot of solar energy on the grid, electricity in the middle of the day will be cheap. And electricity in the early evening when the sun goes down will be more expensive and higher carbon. And so we're going to want to bias electricity use to the middle of the day, and then start to try to minimize it during the evening. We won't need to turn it off per se, but getting this flexible demand, we're able to move demand to different parts of the day when there's lower carbon, lower costs, will be a very big advantage, and be able to be done seamlessly with AI. So that's the ecosystem of buildings is going to start to look quite a bit different than what we've got today, and it will also integrate battery storage into buildings. One of the companies that I was particularly interested in when they were founded, and they've now been bought by Siemens, which is a global company, and they're starting to understand this is a big area, is using AI so that not only do we optimize the building, but we start to include building occupants in how the system works. And so this particular software was polling people in the building, or you had an app on your phone that you could go to say, hey, I'm too hot, I'm too cold. And the system starts to watch patterns of too hot or too cold and adjust of the different occupants and adjust temperatures accordingly. So last but not least, the headline technologies here are batteries and renewables, and we're seeing a lot of that. Renewable energy has really taken off as the prices come down, and this is data for 2020. And if we looked at 2021 through 23, it's only accelerating. And global use of solar photovoltaics and their production is just skyrocketed. Last year and the year before, 80% of new additions to the electric grid globally was with renewable energy. That's solar and wind. A big portion of that, the majority, is with solar. Solar energy is now cheaper than building a new coal or natural gas power plant, and that's game changing. So solar is taking off. The other thing that's starting to take off and is following behind, but will be as significant, is the use of energy storage, batteries. And this is a projection of the cumulative installation of batteries globally. And if you compare where we are today to where we're projected to be by 2030, it's a 15-fold growth in storage just by 2030, and it will continue to grow up until we don't know, but 2050, 2060 will probably be when it starts to level out. So batteries are going to be a super significant and important part of making solar energy practical, and that is we need to be able to use that solar energy. Solar energy is generated during the day. We need to be able to use it at night. So where are we going to see batteries? We're going to see batteries in people's homes. We're also going to see the batteries that are in vehicles set up to be able to connect to people's homes or to buildings. Vehicle to grid, this V2G. And so it could be that our vehicle is charged in the middle of the day, wherever it might be, and then at night the vehicle is used to power the home. It turns out that the battery pack in vehicles is significantly larger than what we use in our homes at night. So being able to leverage the batteries that are in the vehicle for home use is going to be important. We're also going to see batteries in commercial buildings, and I'm working on several projects in the US right now where we're using commercial batteries connected to the building. It's primarily there so that they can be able to buy electricity when it's cheap. And right now in California, where this project is, electricity is cheapest during the middle of the day when there's a lot of solar energy. It's most expensive in the early evening, so we charge the batteries during the middle of the day and then discharge them in the early evening. So batteries can be on buildings without solar because we're leveraging solar that's on the grid in other places. But batteries can also be used at the utility scale, next to solar power plants. So we're going to see a wide variety of configurations of batteries. The other thing is right now we don't see extreme time of day pricing, but this is the time of day pricing that we have in Northern California where I'm based, that in the middle of the day, we're seeing this super off peak, 9 a.m. to 2 p.m., 11 cents a kilowatt hour, and then from 4 p.m. to 9 p.m., 34 cents. So it's a threefold increase in electricity prices. So you can see how batteries alone can make sense. Batteries coupled with solar, especially when it's at your house, you can start to get very low energy costs and extremely low carbon emissions from that. So I did want to talk a little bit about embodied carbon. And this is a growing area. And as you remember, next slide, when we're looking at operational carbon, this pie chart on the left, operational carbon, that is energy consumption, does dominate as compared to embodied carbon. But when we look in the short term, on the pie chart on the right, it's looking at it more of a 20-year horizon. We start to see that the embodied carbon is becoming significantly more important. And if we're able to get our operational carbon down by connecting the building to renewable energy, either on-site or off-site, or maybe we make the building very energy efficient, the embodied carbon only becomes more and more important. So if we start looking at where is the embodied carbon going to, the number one thing is the structural system. And the structural system can be in many cases, most cases, some version of concrete. So there's now concrete additives that are already being used in India and a wide variety of places around the planet where we're able to replace some of the cement with slag or fly ash or even byproducts of agriculture or glass. One of the things that I'm especially interested in and excited about the calcinated clay cement. This is something that's being used in Europe now, and I did leave a little link here, which results in a 40% reduction in embodied carbon, and it doesn't depend on, for example, the fly ash. And fly ash is a byproduct of burning coal, and if we've got a lot of it, we should definitely use it. But there is going to be a day where we don't have as much of that. We're going to have to be relying on other strategies like this calcinated clay. There's a steel company in the US that's now using the electric arc furnace to process steel, and they're buying renewably generated electricity. So they're saying that that steel is net zero carbon steel. I think it's an interesting proposition. You know, we could debate about whether or not it's fully decarbonized, but generally speaking, I think it's very much the right direction. And there's a lot of companies, especially companies that are dedicated to hitting net zero carbon, that are now starting to buy this type of steel and other types of cement that are very low or zero carbon. So I did want to share with you a case study. I'm working on the American Institute of Architects headquarters building. This is in Washington, D.C., a couple blocks away from the White House. And it's a 1970s building that we're going to be retrofitting. And so this is how it was designed in the 70s, as single pane glazing, not very good shading, and the building was designed in a way that's very energy inefficient. So our first step on this was, how can we make it more efficient? We're going to replace all the lighting with LED lighting. We're going to replace the glazing with high performance glazing with thermally broken frames. And a variety of other strategies to make the building more energy efficient. Then we're going to take the natural gas boilers, and this is in fact happening as we speak. This renovation is now under construction. They're going to take those natural gas boilers, they're going to throw them away. They are at the end of their life, and they're very energy and carbon intensive. We're going to replace those with CO2 heat pumps that are put on the roof. After the heat pumps are put on the roof, there is some space for solar panels that are going to go on the roof, and the solar panels on the roof are going to meet maybe 10% of the building's overall energy consumption. So what we're going to do for the remaining electricity consumption that the building requires is there's a DC Power Connect option in Washington, D.C., where you can buy your electricity generation. You can choose your electricity generation from a variety of providers. There's one that's called the Clean Choice Energy that provides 100% wind and solar to the PEPCO, that's the local utility electrical grid. So the AIA is going to select that choice, that option, and all their electricity will be zero carbon electricity. It will result in a 15% increase in electricity costs in their area, because right now that grid is still dominated by the legacy natural gas, mostly natural gas power plants. So they're also thinking about embodied carbon at this building, and the best thing that you can do is reuse an old building instead of tearing it down. So by reusing the building, they're getting a 76% reduction in the embodied carbon. And then they're going to go on to do an offset project to eliminate the rest of the carbon. This remaining embodied carbon that's there, it's the embodied carbon from the new glazing, the new furniture, new carpet, the new mechanical system, and such. So to offset the remaining embodied carbon, what they're going to do is they're going to buy solar panels, and this has already happened, and they've donated them to Habitat for Humanity, which helps build housing for low-income people in Washington, D.C. and Northern Virginia, right next door. And they're going to install those solar panels on the low-income houses, and those houses are now going to be using less electricity from the grid, which is lower carbon, and there's lower carbon emissions. And those lower carbon emissions are going to offset the embodied carbon for the building. So that, I think it's a great way to offset the embodied carbon that does something great for the local community. So I wanted to end with a couple thoughts on why our work matters as people involved in the construction industry. This is a graph of US coal production and consumption. And I just wanted to share it with you because there was a time up until about 2005 that coal consumption in the US was just continually growing. And we now have reached our peak coal consumption, and now our peak consumption has, our consumption of coal has dropped dramatically. And this is the kind of thing that we're going to start to see is we were thinking that it would have to sort of bend down ever so slowly and it would take forever to change, but things can change quite rapidly. We've seen this with the consumption of coal. We're starting to see this with natural gas, and we have seen this in the opposite direction with renewable energy. We have a similar thing in the US that wind and solar have accounted for 75–80% of new additions for the last several years. So much so that General Electric, which is one of our #1 manufacturer of natural gas power plants, have shut down their natural gas turbine manufacturing facilities. And it was a big part of why they are no longer part of the Dow Jones Industrial Average. They're still listed on the stock exchange, it's still a big company and everything, but they're now seen because they've been staggering for several years, in large part because they're power plant business. They're no longer considered to be one of the key indicators of the direction of the US economy. If we look at buildings, there's a similar thing in energy efficiency in buildings. There's a similar thing that's been occurring quietly right under our nose, so to speak. In the US, we have this ASHRAE 90.1 standard. Some buildings in India use it. It's the required comparison when you're doing a LEED rated building. So if we compare ASHRAE 90.1 when it was first started in 1975 to where it is today, and there's actually a 2022 version that was just released, it represents over a 60% reduction in building energy use. And I work on primarily buildings that far exceed the ASHRAE 90.1 standard. So there's still a significant room for improvement. And we've reduced energy consumption in buildings on a per square foot basis. We're starting to see numbers like this where 60% is possible and more. So a lot of the building people that I work with, like building owners, developers, they say, well, you know, can we get like a 5% savings or 10%? In my mind, I'm going, no, we can get a 50% reduction. And when I first started working with Infosys, that's what I told them, and that's what they've been able to achieve. So when we connect this rapid change in how we use coal in the US, and rapid improvement in building energy efficiency with renewable energy, we really get this magic transformation that we're all trying to create and bring together. One of my colleagues at Stanford has created a study for 139 countries of how each one of those countries will transition to 100% renewables by 2050. And it's interesting because what his projection is that there will be 27 million jobs lost, and that is a problem and a tragedy for many families. So if you're a coal worker, an oil worker, those kind of jobs will be phased out over time. But the good news is that of the 27 million lost, there'll be 52 million jobs created. And these are good jobs. That is building out solar infrastructure, making buildings more energy efficient, installing wind power, building batteries or installing battery systems. So we're going to see a lot of growth in this sector globally, and there'll be a significant number of jobs created. And I think, you know, the last thought is, it's interesting because we could say, well, you know, Peter, you know, India is quite a bit different than the US, and I would have to agree with you wholeheartedly. But one thing I'd like you to leave with today is the understanding that there is a growth that's going to occur globally, including in India, in renewable energy and energy efficiency. And I think it's an opportunity and an opportunity for us to make a difference at the same time as just being an opportunity to make a living and make a difference. Thank you very much. And I'd like to end by just saying, challenge accepted. We do have a big challenge in front of us, and we are ready to take on that challenge wholeheartedly. I'm also, I've given my Stanford email. If you'd like to email me and discuss any of these issues, I'd be more than willing to do that.
Thank you, Mr. Rumsey. Thank you, Mr. Rumsey, for sharing the invaluable insights. I now declare the floor to be open for Q&A. I'll request the participants to raise their hands either virtually or drop in their questions in the Q&A box or the chat box. Okay, I see we do have some questions in the chat box. So one of the questions is, Mr. Habe would like you to comment on the use of air drying mechanism to lower the dew point of the air going to the HVAC system.
So can you repeat that? I didn't catch it all, sorry.
Sure. So can you please comment on the use of air drying mechanism to lower the dew point of air going into the HVAC?
Yeah, so lowering the dew point of air going into HVAC, but what kind of mechanical? Sorry, did you hear? Or?
No, I didn't.
Yeah.
The air drying mechanism.
Air side mechanic.
Okay. Okay. So I think lowering the dew point of air going into buildings is a critical part of delivering a healthy building, especially when all humid climates, especially in India, most of the climates here, it's an important part of the solution, at least part of the year, if not the whole year. The way we lower the dew point traditionally has been by cooling the air down. And if we cool the air down to 13 degrees is sort of what a lot of people use, and there's some logic to that. The water will be condensed out, and then we can send that air into the building, and the dew point will be in a healthy range. There are other ways to bring the dew point down, and there are several ways, and some of them use things like desiccants. There's heat recovery. There's wide variety of strategies. And in my career, I've worked on buildings where we've tried almost all of them. And what I found is that as far as reliability and simplicity, bringing the temperature of the air down, either as we deliver it into the space or in the space, if it's more of a residential recirculation system, is the simplest and most straightforward way. And so my focus has been, how do we deliver the right amount of air, not excessive amount of air? How do we lower the loads for the building envelope? And then also have a building that responds to the number of people in it, because we generally are asked to design buildings where there's, everybody's in the building and we're sending in lots of fresh air as if the building is completely full at all times. And now we know post-COVID, especially in office buildings, that we have hybrid working and buildings are not as full as they used to be. And so we need systems that can ramp down and so that we don't spend as much energy bringing the dew point down, whatever method we use.
Thank you, Peter, for that. I think Mr. Abhay has a follow-up question, so I'll request Mr. Abhay to unmute himself and ask the question.
Hello, can you hear me?
Yes, sir.
Yeah, thanks, Peter, for an excellent presentation. Really happy to be in this webinar. Very, very nice, sir. Yeah, I mean, what I was trying to ask you was that, because the dew point in cities like Mumbai in India are very high, maybe 28, 30 degrees centigrade. And if at all we are in a position to bring down the dew point by the use of air drying mechanisms like maybe molecular sieve dryers or maybe detergent, the way in which you said desiccant or so, then the cost of those drying is not going to be very high
Sorry,
because you
Mr.
get a dew point of minus 30, minus 40 degrees in just one pass. So that can be mixed, you only have to dry 5% of the air. It can
Mr.
mix with the air that is going in, and you get a dew point of 22 degrees. Yes, sorry.
I guess there's some disturbance from your end, so you're not completely audible. There's some disturbance.
Oh, I'm so sorry. I'll just,
It's better
is it
now.
okay?
It's better now.
Okay, no. So I was just thinking, if some molecular sieve dryer, which can give a dew point of minus 30, minus 40 degrees, is used for drying maybe say 5% air, and it is mixed with the whole total, the dew point can come down to 22 degrees centigrade, which is lower than your working temperature of 24, 25 degrees centigrade. So any research in this matter, if at all you have any idea, any?
Yeah, I mean, I think the closest thing to that is this idea of, ice storage and driving temperatures down. And I have seen very low temp, low volume delivery systems where they, bring the temperature down significantly to, very close to freezing, let's say 5 degrees for air temperature. And then you have glycol in the chiller system. It's just another way of doing it. I haven't seen any of those ways beat the more traditional way done in its most efficient form. I haven't seen the other methods be able to beat our more conventional way done efficiently. And when I say done efficiently, I mean done with very high efficiency chillers and efficient pumping and efficient air handling. Traditional done very efficiently is very easy to do, and it's pretty hard to beat. So I wouldn't say no, that's not possible, but I personally have not seen that type of strategy or anything similar to it beat a very well designed system that is, bringing the dew point down conventionally.
Thank you very much. Can I have one more question, sir?
Maybe we give some other people a chance, and if there's time, we can come back. Yeah.
Yeah, maybe we can come back to Mr. Abhay again. I'll request Mr. Himanshu Saini to unmute and ask his question.
No, he's logged out.
All right, I think Mr. Saini just dropped out, so we can probably take a question. Okay, Karthik's raised his hand. I'll request Mr. Karthik to unmute himself and ask the question.
Hello, sir. Karthik Prajapati from Beauty Gandhi. I have a question, sir. In India, various regions have a various weather. For example, in monsoon, high relative humidity due to high RH, we have to maintain chiller and we have to produce more generation. So, is it possible by maintaining relative humidity RH by heat pump or by this kind of sources, we can reduce the chiller generation and save the energy?
I apologize. Maybe you could make the question a little bit shorter and then just speak a little bit more slowly, just because it's a little bit muffled. I apologize.
Okay. See, weather on the weather condition, I am asking the question. Various weather condition in India here. For example, in Ahmedabad, in monsoon, there will be very much high relative humidity. So, chiller plant and related building is connected with the various buildings. In monsoon or in weather condition where relative humidity is more, then we have much more load on our chiller plant. So, is it possible to maintain RH in particular building via heat pump, or we can maintain that particular RH in particular building? So automatically the chiller load at generation side will be down, and it ultimately it will result in saving. Is it viable?
Yeah, I mean, I do want to say I've been working in India for 15 years now. My mentor, and I spent a lot of time in Singapore, which is also a very humid climate. I've worked in New Orleans, Louisiana, which is very humid climate. So I'm very familiar with humidity and the load on chillers with high humidity conditions. I've also worked in Chennai here. The load on the chiller is high during those times, and oftentimes it's the dehumidification. It's the #1 load on chiller systems. I'm not quite sure I get your question. I apologize, but we can do dehumidification and controlling RH in buildings in ways that are very energy efficient. And if I could just quickly describe the way to make a dehumidification system efficient. The first thing is, as I said, is we want to lower the load. So we want to deliver the right amount of air for health and comfort. But we don't want to or need to deliver 5 times the right amount of air. So if you look at this conference room where I am now, there's just 2 of us in this room. But if we were doing a engineered design, we would need to size the outside air system for this building to meet 10 or 15 people. But there's not 10 or 15 people in this room right now, there's 2. So we want the amount of outside air in this room to be equivalent or adequate for 2 people. So there's many different strategies like carbon dioxide sensors that we can use to lower the amount of air that comes into a room when there's fewer people there. But once we decide how much we need to deliver into a space, how do we do it in a way that's very energy efficient? And there are a variety of ways of doing that, but generally speaking, what we want to do is we want to cool the outside air that we bring in down to the dew point, and we want to cool it with very energy efficient chillers. And if we look at the progression in chillers, there's air-cooled chillers, there's water-cooled chillers that use a cooling tower, and then there's very efficient water-cooled chillers that use treated wastewater, right? So that it's not using, drinking water. So that we can go from an average kilowatts per ton of cooling of 1.2 to 1.5 all the way down. I was at a chiller plant yesterday that was operating at 0.4 kilowatts per ton for the whole plant. The chiller itself was 0.3. So we can go from, let's say, 1.4 all the way down to 0.4. So we're talking about a 70% savings in delivering cooling to that coil that's now dehumidifying what might be in this room 1/5 the normal air. So in this room right now, it'd be a 90% reduction in energy consumption to dehumidify the air that's needed in this building and keep the humidity just right.
Thank you. Thank you, sir.
Sure, thank you. I think next we can take Mr. Gauransh Agarwal's question. Gauransh, I'll request you to please
hello, am I audible? Yeah.
Yes, you.
Thank you, Mr. Peter, for an excellent presentation. It was very insightful. My question is that nowadays, what we are seeing in the in the new modern world, we are seeing that most of the buildings are very modernistic and have glass facades over it. So what they lack is they do not have good natural ventilation system. So what they do is they use HVAC systems in their buildings, and mostly those are not very good for the environment. Can you comment on some of the passive cooling design techniques that you might have used in your previous projects?
Proponent of hybrid or mixed mode natural ventilation. So if we think about a lot of climates, there are going to be certain days of the year that natural ventilation is not appropriate. So it could be a very hot day, or where I come from, there might be a very cold day, where if you're sitting somewhere near the window, you might be extremely uncomfortable if the window is open. So natural ventilation on those days does not work. But I also come from a climate where natural ventilation, I live in San Francisco, California, natural ventilation for many months of the year is fantastic. And I see the same thing, especially in commercial buildings, where they design fixed windows, non-operable windows, and so there's nothing you can do other than, when you have a lot of glass, sun is shining on the glass, even on a cool day, you have to turn on the cooling system, right? So it is required by energy code in California that the HVAC system can bring in fresh air and not cool it and deliver it to the space. Or maybe if it doesn't need dehumidification, you just cool it a little bit. But I was in a building yesterday here in Bangalore where they had operable windows in a brand new building, office building that was 100,000 square meters. So operable windows are very possible even in large buildings. That obviously in a large building it's quite a bit different than if you were doing residential, either multifamily or single family. But operable windows are not only make sense at certain times of the year, but they also are things that people like. The key thing is that you don't want the window to be left open when it's a really humid day. And that's why a lot of engineers, HVAC engineers, will be reluctant to have operable windows in the building, because if they feel that the windows will be left open on the bad day, the humid day, it could result in high humidity conditions that result in problems in the building, right? Including health problems. So a lot of engineers are like, when they get into the meeting with the architect and the owners, they're like, no, you don't need to do that. But ask any user who's sitting in a building near what would have been an operable window, whether or not they'd like to have an operable window. Every single one of them will say, yes, please. So, and done right, those windows will be closed on the bad days. And so I've worked on buildings where we have either in the pantry area or overhead a little light that will be green or red, or a little message on your computer or your phone saying, today is a good day to open the window. Today is not a good day, please keep all the windows closed. And you can do a little bit of enforcement of that with facilities team can come through the building once a day and either remind people or just close the windows if it's a bad day, or even they could help by opening some of the windows. So I do think that operable windows make sense. Building design also matters, because what we really want is a little bit of a cross ventilation to develop. So if in an area where operable windows make sense, we want to design a building floor plate that's a little bit on the thin side, so that if we open windows on the two sides, we can get some cross ventilation going through, even if there's like a very gentle breeze near the building. So yeah. And if you look at traditional architecture almost anywhere in the world, natural ventilation was an important part of that. So we need to relearn some of the old techniques that were commonplace.
Thank you, sir.
Thank you, Peter. I think we'll take one question from the Q&A box now. To Miss Pavitra has a question, and she wants to ask Peter that Peter talked about the clean energy costs in Washington, D.C. have increased by 15% due to the fossil fuel domination. Her question is regarding what kept the people motivated to choose clean energy over conventional energy in spite of the increased costs.
So good question. So So there's two aspects of that. The first thing was for us, we want to make it affordable. So as you recall, I said it's 15% more expensive to buy the renewable electricity. And so 15% more expensive to buy the renewable electricity, right? So, but the thing to remember is we're cutting their energy bill down. I should have showed the graph. We're cutting their energy bill down through energy efficiency, at least on a kilowatt hour basis, by 60%. So they're going down 60% and then they're going back up 15%. So they're somewhere around a 45% reduction in their annual energy dollars. So that was the first thing that was an important part of the story. So they were very happy about the whole thing. But still, if it was just up to like the CFO, he or she might have said, well, you know, we'll bring that down, you know, and not buy the renewable energy. American Institute of Architects is a organization that's run by architects and represents architects. Architects around the world and in the US are now coming to the realization that their work and their responsibility in this climate change is critical. So what we're seeing is not only architects, but the organizations that represent architects, engineers, and other building professionals changing the way they think about and message climate change. So AIA came to this renovation project with a very high priority of we will decarbonize this building, show us the cheapest way to get there. And you know, that's what we did for them. I mean, the renovation was not for decarbonization. The renovation was they needed a renovation because it was a 60-year-old building. But they said because we're spending the money on the renovation, it will be a decarbonized renovation. So, you know, part of what I say to people like clients nowadays, let me know when you're ready, because if you're not ready, there's so many other companies, organizations that are very ready to change the way they think about building. So I work with a lot of large companies in the US and globally, and global companies that are very ready. And so I'm spending my time right now with those clients that are very ready. And I think for all of us, we understand in the building industry, there's clients that are not ready at all. Some are sort of ready and others that are very ready. So we want to definitely serve and be very focused on the ones that are ready, because they're going to serve as an example for the rest. But the ones that are not ready, there's a wide variety of strategies to make energy efficiency practical and affordable, and we need to show them those technology strategies and those pathways so that bit by bit they start to get more comfortable with it. They might not be ready for a complete change in the way they do their buildings. It might be that we need to work with our clients in the first building and do some, in the second a little bit more, and it's by the third or fourth building that we've gained their confidence and that we can really start to do something quite special. And I think the last thing that I'd like to remind our clients to get them more ready is that the market, that is people who are going to want to lease space in the building or rent space in that apartment, more and more are coming to the realization that, like, hey, I want to be in a green building. So if you take Delhi in the part of the year where the air quality is really poor, there's a lot of air pollution. It doesn't take a lot for somebody who's renting an apartment to say, you know what, I want to be in a building that's more healthy, and I want to live in a world that's more healthy. It's really right there on your doorstep. And especially the younger generation is very cognizant that, you know, something needs to change and I want to be in better buildings.
Sure. Thank you, Peter. I think we can take another question from Mr. MP Agarwal. I'll request you to please unmute yourself and ask the question.
Thank you, Mr. Peter, for a wonderful presentation. I have one question that you have mentioned that AI is being used extensively for HVAC system design. And also, are you using the same for the renovation of the old buildings like American Institute of Architects you have just mentioned? And in what way AI has helped you in that way?
So you said, what was we're using what in buildings?
AI.
What?
Yes.
Oh, AI. Okay. Yeah. Thank you. Sorry.
Artificial intelligence. Yes.
Yes. Okay. It was very close to AIA, American Institute of Architects, and I was like, wait, okay. My apology. Yeah, so it's interesting because, artificial intelligence for use in buildings is, let's just say this, if we're going to say, where is AI globally, just in all areas? I'd say maybe it's no longer a baby, maybe it's an early teenager, chat GPT, AI in buildings is still like in the pregnancy phase, not yet born. So there are little signs of AI starting to be used, or indicators of where we could use AI for buildings. There are indicators like the Nest thermostat, but Nest is not true AI, but they're starting to layer on in the cloud connection to the Nest thermostat. They're starting to layer in some AI, and that is, you can sign up for connecting your Nest thermostat for flexible demand, and so that the utility is actually forecasting weather and it's making decisions about changing your set point temperature a little bit. So there's little elements starting to come through, but it's not yet commercially available in any wide scale form. But I did want to tell you, there is no doubt in my mind that this will be one of the energy efficiency blockbusters. And when I say efficiency, it will also overlap with demand flexibility, which is a little different than energy efficiency. And that is being able to shift when we use energy to different times of the day based on the grid. So I do think that AI will be very significant in lowering overall energy use and creating demand flexibility, but it's not yet there at all.
Just one add-on, sir. See, in India, like ASHRAE, we have an ISHRAE, Indian Society for Air Conditioning Engineers. So there is a movement which we have spread across the country, that why not you set the temperature thermostat 1 degree high. So when we today room temperature is set at 24 degrees, if we set it at 25 degrees, typically it would save about 5 to 6% of the power. So is there any movement of that sort in US also, which you would like to spread?
So modifying the temperature to create flexible demand is something that I do believe makes sense. So let's say during the day in an office building, it's at 24, and then that critical period starts to, and again, this is evolving and each grid is different. But let's say that there was a critical period starting at 4 p.m., similar to what we're seeing in California, changing the set point to 25 from 24 and letting the building coast a little bit. There's thermal momentum. And so you won't really notice as an occupant that much of a change. The thing about energy efficiency that we need to remember is that the vast part of the opportunity is by doing the same but using less energy. So what a friend of mine, Amory Levins, likes to say is, we want cold beer and hot showers. We can still have that thing. We don't really care how, and consumers don't care, how do we cool the beer? How do we create the hot water for the shower? They just want that service. And so my particular focus is delivering the cooling to the space, whatever your temperature set point wants to be, in a way that's very energy efficient. Now, if somebody said, well, I want to keep the office space at 20 degrees, I said, well, wait a minute, that in and of itself is wasteful. But if everybody is accustomed to 24 and they really want 24, I can accomplish 90 or 95% of what I want to accomplish through energy efficiency. And maybe later we have a little discussion about 24 versus 25. So, that's my general approach to energy, is that let's go after delivering these services in a way that is more energy efficient, not changing the service so much.
Sure. Thank you, Peter. Keeping in mind the paucity of time, I think we can take one more question from the chat, and I'll give a chance to Mr. Abhi after that question. So Peter, here's a question for you. Based on your experience, whether having a decentralized or a centralized HVAC system, which is best when accounting for embodied carbon, reducing complexities, future aspects like water shortage?
Yeah, so there is no one answer for that about centralized versus decentralized HVAC system. It does depend on the type of building and the climate and a wide variety of other things. But if we just take an office building, for example, the question was about embodied carbon of the HVAC system, just so so a centralized HVAC system in an office building means that we would have a chiller with a refrigerant in it, and then we would pump chill water around the building and then air handlers and such. Versus decentralized could be that we've got individual units that have refrigerant in them and they're all over the building, or there's split systems, some version of like that. It turns out that the embodied carbon of mechanical or HVAC systems right now is dominated by the refrigerant, assuming that a certain percentage of that refrigerant is going to leak. Refrigerant is a very strong and powerful greenhouse gas, and we have to do everything we can possibly do to first make the size of the refrigerant smaller, but secondly, to try to avoid having that leak out. So assuming that some will leak out, having a smaller amount of refrigerant, which can be done with a centralized system, usually results in significantly lower refrigerant, is going to be the lower embodied carbon. And it also turns out that chillers now have new refrigerants that are only available in chillers that have very low global warming potential. There's this new HFO refrigerants that are only available in chillers that have a GWP of 1, as compared to 4,000 for a split system that's using R410A. So I generally would be in favor in larger buildings of centralized, but if we get into something like an apartment building, different things like that, the solution might be a little bit different. Answer one question I see in the chat. Why was there presence of benzene in cooking gas flue? There's a study that you can just Google Stanford cooking benzene, and you'll see the study. And there's some articles that were written in the Stanford newsletter about that. And that was just released 6 months ago. When you burn natural gas, there's two things. There are impurities in natural gas. Natural gas comes to, or propane comes to the burner in a filtered form from wells and then filters and processing plants. Typically, it's not pure methane. And then there's also incomplete combustion. So not only is there benzene, and that could be because it was not filtered properly or fully, or it could be that it's in the air, that when the combustion is happening, there's a reaction that's creating it. You can read the Stanford paper there, explain it. For the same reason we get carbon monoxide, nitrous oxides, and formaldehyde.
Thank you, Peter. I think keeping in mind the time, that would be the last question that we could take. So I'll close the Q&A session. And as we come towards the end of our webinar, on behalf of the AEEE team, I would request Dr. Bhaskar Natarajan, Senior Fellow AEEE, to extend our vote of thanks to our esteemed guest speaker, Mr. Peter Rumsey.
Thank you so much, Peter. As the audience has mentioned, it was indeed a delight to hear you talk. Packing your decades of experience into 1 hour, I'm sure, is the biggest challenge you faced. I'm sure there is a lot more that you can share with us, and we hope there will be other opportunities to interact. The challenges as we go forward into 2030, 2050 are many. And as you have indicated, things are about to change very rapidly in the next 4 to 5 years on all the areas that you mentioned, whether it is AI, whether it is materials, whether it is control systems. And it would indeed be excellent to work with people like you to make sure that these things happen faster. Indeed, thank you so much once again. And thank you to the 100+ audience who have been with us. Please do share with us any specific questions that you may have with AEEE. We will try to see if we can reach out to Peter to respond to as many of them. So thank you once again, Peter, for your excellent sharing of your knowledge and experience. Thank you.
Yeah, thank you very much.
Thank you, Dr. Bhaskar. Lastly, I would like to thank our participants for their time and active contribution towards today's webinar and engaging dialogue. I once again thank all our partners, ISHRAE, India Cooling Coalition, Solar Decathlon India. Thank you, everyone.